Now that we have our 5 basic functions down, we are going to start transforming these parent functions into transformed functions. The first transformation we'll be looking at is the vertical shifting. So let's say I have an f of x parent function. It should say k is just a number. If I have f of x, that parent function, plus k, when I add k to the function, the graph shifts up k units. But when I subtract k, this should say from the function, the graph shifts down k units. Looking at our first example, I have our parent function f of x equals the absolute value of x. That's a parent function. You need to know that it's v-shaped, and we're going to go ahead and graph that parent function in green. I know that my vertex is at 0, 0. To get to my key points, I'm going right one, up one, and left one, up one. And then I know that it's v-shaped, so I should have straight lines. And that's my parent function of f of x equals the absolute value of x. Next, I'm going to do g of x, and I'm going to be doing this one in purple. I have the absolute value of x, which is the same function as the green function, but this time I'm adding 2. What does adding 2 do to our parent function? Well, from our steps above, we said if we added a value, it shifts our graph up, in this case, 2 units. If I take my vertex and I shift it up 2 units, notice that my new vertex is going to be at 0, 2. From that new vertex, to get my other points, I'm going to go right one, up one, and left one, up one, because that would also shift up these points 2 units. Connect your lines to create another v-shaped function, and the purple function does look like it's the green function, only shifted up 2 units. The third function, h of x, equals the absolute value of x minus 3. Notice we still have that same green parent function, except this time I'm going to be shifting down 3 units. The reason I'm shifting down is because I have a minus on the 3. So I'm shifting down 3 units. Going back to my green parent function, if I shift the points down 3, notice your new vertex is going to appear at 0, negative 3. To get my other points, I can go from my vertex right one, up one, left one, up one. Or another way you could think about it is if you could move those 3 points down 3 units each, you'd have these 3 critical values, and then you can draw your V shape. Our next example using vertical shifting is using the parent function f of x equals x squared. Again, I'm going to do that in green. I know that the shape of my x squared is a U shape. That's something I have to memorize. I have a vertex at 0, 0, and key points at 1, 1, and negative 1, 1. Notice that these are the same key points as your absolute value, but because you know that it's U-shaped, you're going to connect them with a U shape instead of trying to connect them with a V shape. Therefore, you're getting a quadratic function instead of an absolute value function. So just be careful of your shapes, please. G of x is equal to x squared plus 3. This plus 3 on the outside tells me that I'm shifting up 3 units. When I shift my vertex up 3 units from 0, 0, my new vertex would be at 0, 3. Then you can shift your key points up 1, 2, 3, 1, 2, 3. Notice from the vertex, I'm still going right one, up one, left one, up one. It may look like it's a little bit skinnier. It's really not. It's only that you're seeing less of the graph. H of x equals x squared minus 5. The minus 5 behind the parent function x squared tells me that I need to shift down 5 units, making my new vertex at 0, negative 5. So I shift down 5, If I shift my key points down 1, 2, 3, 4, 5, and again over here, I can see that we have this parent function shifted down 5 units. Another way of getting your key points is if you shift your vertex down 5 units, from your vertex you could get the other points just by going right 1 and up 1, or left 1 and up 1 from that new vertex. So those are some examples of vertical shifting. Next we're going to be covering horizontal shifting. If we let f of x be any parent function, and this should be h, and let h be a number, and I'd like to graph y equals f of x plus h, notice that this is different than the vertical shifting because the plus and the minus is happening inside the parentheses, whereas on the vertical shifting, the plus and minus was happening outside of the function. When the adding or subtracting happens outside, we're going up and down. When the adding or subtracting happens on the inside of the parentheses, we'll be moving left and right instead. So if I add h, not to the function this time, but if I'm adding h to the variable x, then the graph is going to shift either left or right. And your intuition says plus seems to be like to the right, because that's where our positive values go. Unfortunately, this is opposite of what your intuition might tell you. It's actually going left h units. Similarly, when we subtract h to the x value, not the function, but the actual x inside the parentheses, the graph is going to shift right h units. Notice this is opposite of your intuition, or what you might think happens. We have some examples for you. On the first example, we have f of x equals the absolute value of x. You have to know that that shape is like a parabola on its side cut in half. This shape right here, this branch. I have to know that my vertex is 0, 0. I have to know that I have a key point at 1, 1, or right 1, up 1. And then you can sketch the rest of your graph. It's not going to be a perfect graph, but it will be good enough for what we're doing. For the next graph, g of x, notice I still have the parent function, but this time I'm adding 1. Notice that I'm adding 1 underneath the radical, which means it's connected here with invisible parentheses. So because it's inside and being added to the x, not being added to the function, I am going to move left 1 unit. Plus 1, you would think goes right 1, but it actually goes left. On the inside is opposite of what you might think. So if I take my vertex and I move it left 1, my new vertex is going to be at -1, 0. Notice it's the x value this time that is being shifted. To get to my next point, either I can move the key point over 1, or I could go right 1, up 1 from my vertex, and then I can sketch my graph. My third function, h of x equals x minus 3, because the minus 3 here is being added or subtracted to the x, I know I'm a horizontal shift. Because it's being subtracted, it's opposite of what your intuition might tell you. It's actually going right 3 units. If I go right 3 units from my parent function, which is the green function, I get a new vertex at 3, 0. If I shift the key point over, I have a point at 4, 1. Another way you could do that is just to go right 1, up 1 from your new vertex. And then you can sketch your square root function. Our next example's parent function, f of x equals x cubed, looks like an N-shaped. On my graph, I have a vertex at 0, 0. To get my key points, I either go right 1 and up 1, or left 1 and down 1. From there, that can either look like an S shape or an N shape, so you got to be very careful about how you draw this. In this case, we have an N shape. Now again, that's not 100% perfect, but it's good enough for the purposes that we need for. G of x is equal to x plus 3 quantity cubed. Again, it's a cube, function, so I still am using the same parent function, but this time I'm adding 3 to the inside. Adding 3 is opposite of what you might think. It's left 3, and that's a shift left 3 units. My new vertex is going to be at -3, 0. If I shift over the key points, left 3 units, I can sketch my cubic function. H of x is equal to x minus 2 cubed plus 4. This is the first time we're doing two transformations. We got a minus 2 on the inside of the parentheses, but we've also got this plus 4 on the outside of the parentheses. We've talked about both of these transformations. They're both shifts. On the inside of the parentheses, that's going to tell us that we go left and right, opposite of your intuition. Minus 2 seems like you'd go left 2, but minus 2 actually goes right 2 units. On the other hand, the plus 4 is on the outside of the parentheses. We're adding it to this function, so we're going to be moving it up or down. Plus 4 is exactly what you might think it would be. It would be up 4 units. So that one goes up and down. The inside of the parentheses goes left and right. The outside of the parentheses go up and down. The inside of the sign is opposite of what you might think. The outside sign is exactly what you would think. Positive goes up, negative goes down. So I have two shifts that I'm going to be working with. If I look at my vertex at 0, 0 for my parent function, and I shift it right 2 units, but also up 1, 2, 3, 4 units, I have a new vertex at 2, 4. 2 from the horizontal shift, 4 for the vertical shift. Now I can shift my key points right 2 and up 4, or I can just use the key points from my vertex going right 1 and up 1, or left 1 and down 1. Now I can sketch my graph, and the blue function does look like the green function, just shifted right and up. Our final transformation is vertical stretch and compress, and we're also be talking about reflections in this as well. Notice in this case I have y equals a times f of x. So in this case I'm being multiplied. In the vertical and the horizontal shifting I was adding or subtracting to either the x or the f of x. In this case I'm multiplying to the function out in front. When multiplying the function by a constant value, which in this case we'll call a, the graph gets stretched or compressed. And this is getting stretched or compressed vertically. So to graph, we will multiply the y value of the key points by the value a. The reason we multiply it by the y value is because this is a vertical stretch. So the y value is getting stretched either vertically or compressed vertically. When multiplying the function by a negative value, the graph gets reflected. So we can do both the compress and the stretch and the reflection all at the same time. To make this a little bit more clear, we're going to look at our first example. Our parent function on the first example is f of x equals the cube root of x. You have to memorize that your key points and your vertex are 0, 0 for the vertex and 1, 1 and -1, -1. Or you can think of it as right 1, up 1, left 1, down 1. I know that this shape is S-shaped, similar to my N-shaped cubic, but it's more horizontal. So for g of x equals 2 times the cube root of x, notice I still have the cube root of x, which is still this green function, but I have the whole value multiplied by 2. Because 2 is greater than 1, the coefficient of my f of x is 1, so because 2 is greater than it, I'm going to be getting bigger or taller, which we're vertically stretching all of the points of the graph. If my value coefficient here was something less than 1, but still greater than 0, for example a half, I'd be getting closer to the x-axis, or shrinking, what we call a vertical compress. So because a is equal to 2, and because it's greater than 1, I know I'm going to be stretching. Because I have no adding or subtracting to my function, my vertex is not being shifted at all. My vertex stays the same at 0, 0. What does change is because that I have an a is equal to 2, I'm going to be multiplying my y values of my key points by 2. For example, to get the key point of the green function, I just went over 1 and up 1, right 1 and up 1. So instead, because my a is 2, I'm going to be going right 1 and up 2 instead of right 1 and up 1. Similarly, instead of going left 1 and down 1, I'm going to be going left 1 and down 2. All of my values get twice as far away from the x-axis because my a is 2. And then I can connect my lines here to get a cube root function that's transformed by being multiplied by a. The third graph, h of x equals negative the cube root of x cubed, tells me that I have an a of negative 1. Well, when I have an a of negative 1, that means my graph is getting reflected. Again, I have no shifting. My vertex still stays the same at 0, 0. But I'm going to be multiplying my y value of my key points by negative 1. So instead of going right 1 and up 1 on my green parent function, I'm going to be going right 1 and down 1, because a positive 1 height multiplied by negative 1 is negative 1. Instead of going left 1 and down 1, my height here is negative 1. So when I multiply negative 1 by negative 1, I'm getting positive 1. Notice that your graph is reflected over the x-axis here. So in summary, my green function is my parent function. The purple function got stretched twice as high. Each of those points got stretched twice as high or twice as low. Another way of saying that is twice as far away from the x-axis. On my blue h of x function, I'm being multiplied by negative 1. So all the points above the x-axis now come below the x-axis. All the points below get reflected above the x-axis, and that's because my a is negative. So that one was a vertical reflection. On my next graph, I have f of x equals the absolute value of x, and that's another one that we've already done before, the absolute value. It's a V-shaped. You have to know your vertex is 0, 0, and your key points are right 1 up 1 or left 1 up 1. Connect your lines with a V shape, not a U shape. You got to be very careful with your key points there. On the next graph, g of x is equal to negative the absolute value of x. I know that my a is negative 1. And because my a is negative, that's a reflection. My vertex doesn't change at all because I have no shifting. So my vertex is still 0, 0. Instead of going right 1 and up 1, because my a is 1, I'm going right 1 and down 1. Instead of going left 1 and up 1, I'm going to go left 1 and down 1. I'm multiplying my vertical values, or my y value, by negative 1. Notice this just looks reflected over the x-axis. h of x equals 1/2 times the absolute value of x. Notice I have an a of 1/2 because 1/2 is being multiplied. I still have my parent function of absolute value, but all my y values are going to be multiplied by 1/2. This is what we call a compress. Instead of a stretch, g of x equals 2 times the cube root of x was a stretch because 2 is greater than 1. Because in this case, 1/2 is less than 1, yet still positive, we have a compression, meaning it's getting closer to the x-axis. Now, it's not that important that you know the difference between a compress and a stretch, because you really do the same operation. I'm still taking my vertex, which is 0, 0, stays the same. To get to my key points, instead of going right 1 and up 1, I'm going right 1 and up 1/2. Instead of going left 1 and up 1, I'm going up left 1 and up 1/2, which makes my V shape much flatter or wider. Technically, the graph is not getting any wider. All the points on this green line are just getting pushed down. They're half as tall as they used to be. So all the points are getting pushed down, so it's really more flat than it is wide. because we're talking about a vertical stretch or a vertical compress. So that concludes our three types of transformations: the vertical shifting, the horizontal shifting, and the vertical stretch compress with a reflection. Next, we're going to put all of these together and give you several examples.